All right, so like we said, the most important thing with work energy theorem questions is interpreting the context of the question, okay? And that is figuring out what kind of energy is changing, what we've got to find here. So we got a box with a mass of 8.5 kilograms that's lifted above ground level, and 183 joules of work is done. How high does the box get? What kind of energy are we changing in this question? Potential energy, because the height's changing, okay? And they tell us the amount of work that's done. So am I going to need to use like force times distance here? No, I'm not. Okay, I already know what force times distance equals because they told me there was 183 joules worth of work. This is about as easy as a change in potential energy question could possibly be. All right. What about number 2? I got a soccer ball, mass 0.75 kilograms, kicked from rest to a speed of 21 meters per second. Kinetic energy is changing there, and this time they're asking us to calculate how much work is done. So again, do we need the force times distance at all here? No. Okay, again, this is as easy as a kinetic energy question for work energy theorem could possibly get, because you did not have to use force times distance in either one of these. All right, on an exam, I would guarantee you that they would not be this easy. I would have the force times distance part in there for sure. All right, and that's what we'll do on probably on Tuesday's quiz. Okay. All right, so for question number 1, okay, give them a mark if they had work as a change in potential energy somewhere. Okay, and they may have, I kind of shortened it here, but they may have written it like this: work equals MGHF minus MGHI, but I've shortened it because MGHI is what? 0. Yes, Kyle, question? You are absolutely right. It is. That is so strange. Okay, well, let's do it up here then. Okay, so give them a mark for their givens. Let's say givens first here. All right, so 8.5 kilograms. Okay, and work is 183 joules. Okay, and obviously we know G because it's on our formula sheet. All right, so 1 mark for that. Okay, 1 mark for works to change in potential energy. Okay, so they may have written this. Okay, so we're trying to figure out how high the box gets. So this is 0. Okay, we divide both sides by mg. Right, so give them a mark if they got to that formula. So we're up to 3 marks now. Okay, or they may have just plugged their numbers straight in. If they did that, that's fine. So 183 joules, okay, divided by 8.5 times 9.81. Okay, so 183 joules, okay, divided by all right, so the box gets to a height of 2.19 meters. If they rounded it to 2.2, that's fine. Okay, so that'll be their 4th and final mark. They must have meters on there, guys. If they don't have units, it's not right. Okay, questions on that one? Everyone's good with that? Okay. All right, soccer ball, mass 0.75 kilograms, kicked from rest to a speed of 21 meters per second. How much work is done? All right, so 1 mark for givens, and we're going to say this one's out of 4 as well, guys, because I've got 4 marks on here. I don't know why there's a 3 there. Okay, so mark for givens. They've got works to change in kinetic energy. They can have a mark for that. Okay, that would have been 1/2 mvf squared minus 1/2 mvi squared. Obviously, since it's kicked from rest, that's 0. Okay, so all we have to do is plug in our numbers on this one. There's no manipulation. It's already set up to solve for the final kinetic energy and thus the work that would be done on the ball in kicking it. So another mark here for plugging in their numbers: 1/2 times 0.75 times 21 squared. Okay, and their fourth and final mark will be for the 165.3755 joules. So if they have 165.4 or 165.38 joules, okay, that's fine. As long as they have the joules on it, okay, it's good. Questions on that one? Okay, make sure your name is on it. Put it in the box. Okay, so on number 10 here, guys, if a person jumps out of a plane, okay, assuming the plane's not moving forward, it's a helicopter, it's just hovering there, okay, it only has what kind of energy? Only has potential. So the person inside also only has potential energy, okay? So we want to figure out how much he has when he's at that height. So EP is the thing that's unknown, but we know the formula for that is m times g times h. Well, we know the person's mass is 55 kilograms, and we know the height is 1,250 meters, and we know 9.81 is always present. So, okay, we just go 55 times 9.81 times 1,250. Now, when we do this, we get 4375 or something like that. Like, you get a big long number. I put it in scientific notation to shorten it. It's force of habit to do that for me, and because I do that in physics all the time. So if you got, I think it was something like this for the actual long answer, you did it right. Yeah. And then for number 11, we take this number and we use it now for our kinetic energy, because when you jump out of a plane, your potential energy rapidly changes into kinetic as you fall because you speed up. Right? Okay, so according to the first law of thermodynamics, the law of conservation of energy, which we're going to talk about tomorrow, I can't gain or lose energy unless I do work on something. All right? Since while I'm falling, I'm not doing any work on anything, when I hit the ground, I should have the same amount of energy as I had when I left the plane. It's just now no longer potential, it's all now kinetic. Once I hit the ground, then I'll do work on the ground. And that'll definitely leave a mark in the ground shaped like me. Okay, so what I'll have then is that my kinetic energy equals that 6.74 times 10 to the 5 joules. Okay, we still know his mass is 55 kilograms, and that's all we need to know in order to figure out how fast he's going when he hits the ground, because kinetic energy equals 1/2 mv squared. All right, so if I want to get v by itself, I just divide half of m over to this side and take the square root. Okay, so we'll have our 6.74 times 10 to the 5 divided by half of 55 square rooted, and that should give us our 156.6. Yeah. Any other ones there, guys? 13? All right, so if we're climbing the face of a cliff and we've ascended 400 meters, have we done some work? Absolutely, it's hard work to climb, okay? And as a result of your climbing, you've gone from having no potential energy at the bottom of the cliff to having a fair amount of it 400 meters above the bottom of the cliff, okay? So he has this much potential energy because he's done that much work. But it doesn't really matter about the work part for this question. This is how much energy he has. Okay, I'm looking for his mass, and I know his height. So I can simply go EP equals m times g times h, and solve for m by dividing both sides by gh. Okay, so when I plug in my numbers, I'll have my 2.55 times 10 to the 5, which you enter into your calculator just like Avogadro's number. Okay, divided by 9.81 times 400. Okay, so when you punch that into your calculator, okay, all right, you're going to have, it's going to look kind of like this. So we'll go brackets 2.55, okay, and then you hit the second function and the comma, so you get the e to the 5. All right, and then we're going to go divided by 9.81 times 400. Okay, so we get that he has a mass of 65 kilograms. Does that make sense? Okay, any other ones? All right, keep going there, guys. Okay, so we're looking at trying to find the mass of a cannonball that is moving at 80 meters per second and has 99,200 joules of energy. What kind of energy is this? It's kinetic because it's moving. Okay. In that way, it's also mechanical, but we'll leave that for another day. Okay. So I know the kinetic energy of the cannonball is 99,200 joules. So that's how much work the powder and the explosion inside the cannon would have done in order to get it to this 80 meters per second that it's moving at. All right. So EK equals 1/2 mv squared, and I'm looking for m. So how do I get m by itself? Am I multiplying all three of these together? Okay, so if I want to move things, I do the opposite. Okay, now I've got m by itself. All I got to do is plug in my numbers. So I'll have 99,200 divided by 1/2 of 80 squared. All right, so if I punch that in, okay, I'll have 99,200 divided by 0.5 times 80 squared. 31. Yeah. Okay. Don't let the squared confuse you, guys. You still move something over, okay, with the exponents on it, right? If you're looking for it, then you'll have to square it. So if I'm looking for v, then I have to square root what I'm doing. If I'm not looking for v, I move v squared in its entirety, okay, without changing it. Okay, so on number 15 here, okay, our anvil, and we have to transfer the mass down here because it's the same anvil, okay, is 35 kilograms. All right. It has 10,000 joules of energy when it hits the ground. What kind of energy does it have when it hits the ground? Kinetic, because it's hitting the ground. It can't have any potential because its height is 0, and it's been falling and building up speed the whole time. All right, so we know that the kinetic energy on the ground is 10,000 kilograms, or 10,000 joules. Sorry, not kilograms. All right. What speed will it hit the ground at? Well, EK is the only kind of energy it has, and that equals 1/2 mv squared. So I divide both sides by 1/2 of m, and then what? And then square root. Okay, that'll give me v. So when I plug in my numbers, 10,000 over 1/2 times 35. Okay, so 17.5. All right, and then you square root that, and you should get 23.9 meters per second. Okay, is that making sense? Okay, any other ones? All right, keep going.